Hello, everyone. My name is Nijesh. I think I'm all excited as you all are to present this session, which is entitled Operationalizing GenAI, the effective set of LLM compression optimization methods. So just a word about me is I work as an AI engineering lead at IBM Singapore. Apart from the regular AI and LLM world that I am in, I do love math and coding, and I have my passions in terms of yoga and hiking. If you all are into one of these, I think you would find me as a companion. I love reading a lot of books. I'm a voracious reader. And I love listening to music, and I play a bunch of instruments. Here are my LinkedIn credentials in case you want to connect after this particular talk. And everything that I'm going to share here has already been shared in the GitHub repository. So you would be able to go through all of these if you miss on any of them. So the agenda for today is taking you through some of the model compression, specifically in terms of LLM compression and optimization techniques. And these are coming from some of the projects that we have been doing as part of my own personal projects, as well as part of my job and some other experiences. So I would try to keep it as succinct as possible, given the time that we have. Although the text that I have prepared actually is pretty much detailed. So in case I miss out on something as well, you can be rest assured that you can have a reference material like kind of a material in the GitHub link that will be shared later. So we'll go through this introduction to building a GenAI application. We'll look into some of the challenges that are there in operationalizing GenAI. We'll go through some of the compression methods and optimization, and we'll see what case study we can go through. Just to start the whole it's about how the applications are built. I think most of you who would be attending, you really know what a GenAI is. It's actually a branch of artificial intelligence which specifically deals into generation of audio, code, images, text, and simulation. Although generative AI is not just about generating the content, it is also about encoding it, because the transformer architecture, which is the backbone of all of these, actually has both the encoder and decoder part. So it's kind of a subset of a deep learning. We have been doing machine learning for quite a long time, and stat modeling before that for a long time. So it's a subset of deep learning to start with. So you can think of a language model as some kind of a next word predictor. So if I give a bunch of words to it, it will predict the next word. So maybe a Kobe Bryant was one of the best players of NBA and all that. You can just go ahead and or Sachin Tendulkar has scored more than 100 centuries in what. So if it's basketball or centuries in this case, it's more around how we predict the next word. Now, it's not just limited to just predicting text. It is also being used in the code world, in natural language, in computer vision and all. But the talk that we are all interested about is to know how do we productionize these things and what are the challenges behind that. So this has been taken from the following website, and this actually succinctly gives you an example of a generative AI application, which is very popular, which is called retrieval augmented generation. So in short, what it does is it actually gives, when you ask a question, it gives you an answer, and the answers are much more contextualized to the kind of documents or the internal documents that you give. So it's kind of chat with PDF kind of a thing, or chat with internal documents use case, which is very popular in terms of the LLM. Now you can see this neat little diagram here, which actually has the input and output, the guardrails. It also has the retrieval steps and storages, and a lot of other observability matrices. It's good to see, and if you open something like a chat GPT and ask a question, you would get an answer, and it all looks hunky-dory. But if you have to build something like this and productionize it, scale it up, it requires quite a lot of task, because there are a lot of problems that comes with this kind of situation, this kind of application. And some of the things are obviously cost related, and some are more than that. So for example, there is obviously straightforward complexity if you choose a bigger model, let's say a 108 billion model or a 405 billion Llama 3 model. In order to productionize it, it requires a lot more hardware in terms of the GPU, in terms of how you actually make it available to the user. Now, there's also a lot of latency and throughput challenges, which means to say that if you ask a question for a Q&A, and if you're getting a lot more, we are bombarded with a lot more tokens. Now, tokens are the terms that we use. So if you see a lot more words splashing on your screen at a real remarkable rate, we measure those things as latency, and technically it is called time to the first token. And there are other set of matrices. The number of tokens generated in a specified amount of time is also, it also implies a throughput. So you really need to have a low latency and a high throughput kind of an application. So, but the larger the models are, the more other challenges. So we have to go through your pipelining optimization, obviously hardware constraint that we're talking about. So if you go through all of these, it's not very easy to operationalize a model that you would have liked. So what are the practical ways of doing things? So there are some challenges in operationalizing GenAI. So if I can just quickly summarize some of these, there are challenges in terms of the model size and complexity, how you manage the data, how do you scale those applications in terms of the users, the CI/CD platform, and also how do you monitor and maintain that. So for example, these GenAI applications comes with an inherent risk. So it has to be monitored for drift, for bias, for performance, for things like maintenance, for things like hallucination, for things like hate abuse and profanity, uh, prompt injection, jailbreaking, and a whole lot of other things which comes in the purview of ethical and responsible AI. So you need to put some risk and control practices there. But our talk more around is how do you operationalize this in terms of to make it much more performant and much more cost effective. So in terms of that, you're looking at model size and complexity and inference optimization as the major challenges. Because if you select a model and you just put into production, the first issue that you would have is how do you actually cater to multiple users across multiple personas, multiple sessions, multiple logins. So a lot of engineering goes behind the scene to make it happen. So you need to understand how the LLM memory footprint works. And I think people who are part of this call would know that there is something called as the whole KV cache conundrum. So that the thing here is, if you look at this diagram, which actually talks about two different stages. It talks about the prefill stage and a decoding stage. So if I say, what is the capital of, let's say, India, what's the capital of, let's say, Australia, and these words essentially are broken down into tokens, and all of these have to be used to compute what is called as your whole attention vector. Now there are multiple subvectors which are called query, key, and value. So these need to be computed so that you can predict the next token. So the prefill stage is where you actually prepare these states, thereby computing these KV values. And decoding is when auto-regressively you go and keep on predicting the next token. So two main problems with this LLM memory footprint is the model weights itself. So for example, if you have a Llama 3 8 billion model, approximately if you're going with a half precision, which we call as floating point 16 or a BF16, it approximately requires around 16 GB of memory. If it's Llama 2, it's around 14 GB of memory. And this memory, which I refer to, is the GPU VRAM memory. So that's a bare minimum to load with. And then on top of that, we also have a key value cache that needs to be maintained. Because if you look at this key value cache on your screen, you can see that it keeps on populating like these. So we have query, and then for each of the subsequent token, the key query, so the key and values are computed, and finally it arrives at the third layer of attention. Now, and these are all dot product. So if you want to compute these, so per token, as you see on the screen, it's actually number of layers in the attention, so a number of layers in the network, and into the number of heads into dimension head, which is nothing but the KV metric size itself, and the precision, which means to say if it's FP32, the number of bytes required is 4 bytes, and if it's not, it's 2, and so forth and so on. So for one token, if this is the total amount of memory needed, then the moment you scale this up, imagine if you're building a chatbot application, people are actually firing these, and this scales up like anything. So you have very less leverage at how you want to manage your memory, because you have these model weights, and now we have this KV cache that essentially sits on top of these VRAMs, and now whatever is left needs to be the decoder stage memory that you have. So we hence need something called as compression, because although we are not compressing it drastically, we need a technique to manage these computational requirements. So compression is just a way of representing uh, your model in a different kind of dimension, which reduces their resource constraint and computational constraints. So in a way, it is just to reduce your size and computational requirements. So some of the techniques that we'll be looking at right now today will be like things like quantization, pruning, things like knowledge distillation, and low rank approximation. These are just a few of the techniques that we know. There are many more than these as well. Now, if you look at the quantization itself, you can see on the right hand side there are different representation of floating point what you call formats. So we have FP32, which is called full precision, FP16 half precision, and BF is a representation or a modification of FP16. It all depends in the way it is represented, and the ranges also vary. So in simple words, if I am reducing the precision of my weights, because it's all neural networks, which means it's all bunch of numbers, and these numbers are comprised of the weights, which are again numbers, biases, numbers, activation, numbers. So the way you represent these numbers in a reduced precision format is what we essentially call as quantization itself. So you can see that if different kinds of values or different kinds of floating point representation have different dynamic ranges. And you can see this diagram on the right hand side shows a bunch of distribution of values before and after the quantization. So essentially what you're doing is you're just shrinking those values to a lower representation. The range you're shrinking, and there are different ways to shrink that. There are two very popular way of doing quantization. One is definitely the quantization aware training, which is not very popular because it's expensive. What it does is when you are training itself, your errors and other things are computed with the quantization in consideration. So you're actually doing those operations during the training itself, which means when you're pre-training LLMs, you are taking care of all these things, which will have minimal performance degradation. But the most of the things that we are aware of are around the PTQ one, which is a post-training quantization, where you directly convert. Once you download those model weights, you would have seen that there are formats like GPTQ, Auto GPTQ, GGUF, GGML, and all that things. So these are different formats for representing these PTQ values. It's just a bunch of what you call a way of converting an FP32 to an FP16 or an FP16 to an int4 or an int8. That is the reason you can run a Llama 270B or Llama 370B model on a instead of a 4 GPU. Let's say those GPUs are 800 GPUs. From those 4 GPUs to a single GPU or in a collab notebook. That's the reason why we can run that. If you're interested, I have a detailed blog on that, and NVIDIA is a much better blog, so you can read through that. So once you quantize this, the other things that can happen around these is something called as pruning. Now, these neural networks, as I said, are a bunch of weights. So all these weights will not have a lot of influence when you're looking at the generation part. So some of these will have more influence as compared to others. Now, these before and after things that you see, these are some of these weights are very close to zero. So sometimes you can just reduce that to get to prune the network. And pruning is not very new to us. If you are part of machine learning for some time, I think we have been doing that for tree-based methods for some time. And this is a version of that inside the deep learning network. So there are different kinds of pruning techniques. One which is very famous is something called as sparsity, wherein you are actually representing these sparse matrices. So you have a lot of these numbers. There are a lot of numbers that tends to zero. They are near zero numbers, so which are represented by these white boxes here. So you compress those matrices. So a sparse matrix becomes a compressed dense matrix, and this is the way in which you convert that. So the approach that we used is just by using magnitude-based pruning. Now, there are different types of pruning, but I think given the time that we have, the two things that you should be aware of is structured pruning and there is an unstructured pruning. Now, unstructured pruning is what we just saw when we are just targeting the individual weights, just creating an irregular sparse model. So, for example, you look at all these non-zero ones or the one which is tending to zero, and you try to replace it with zero from a magnitude perspective. So it's all over the place on a network. Structured pruning is more about looking at some of the neurons as part of the layers, and you remove some specific layers by scaling things up, which means to say that you are intentionally doing that, and you're removing some layers at all. So this actually has pros and cons. Unstructured is much more much more understandable in a way, or it's much more comprehensible. But structured pruning obviously has its own advantages. Now, if you are some person who really would like to go and understand how pruning works, I have an implementation of this, and I think this is a very simple implementation to make you understand that how the pruning looks before and after. So you can see that before this, the FC3 weights that we are talking about. So this is what FC3 and all. So for example, and you can see here FC1, FC2, FC3. So 3-layer network is a simple neural network. And if I just represent and I create this, if you run this, you will get this output. You can see that all these non-zero ones, very close to 0 ones, are being replaced by 0 ones. So this is an example. All this code is available in the GitHub. You can go and try it yourself. The other kind of techniques that we use, and it is very popular, is something called as knowledge distillation. So you can think of it as simply a teacher teaching somebody, a teacher teaching a student. So we have a teacher model, which is a master model, and we have a student model. So if you want to productionize, let's say 170 billion, or let's say 300 billion or 405 billion model, sometimes it is not the ROI that you get out of it, and the cost that you invest is not justifiable. So the kind of output you want, what if you have a technique that it gives kind of similar output but with a reduced cost? Let's say if you're productionizing a Llama 3 8 billion model by learning from Llama 3 405 billion model. So for the use case that you have identified, you can do something called as knowledge distillation. And these are basically 3 parts where we have response based. So if I want to mimic the output of a teacher model, I would go for response based distillation. If I want to actually use the similar kind of intermediate layers, and this is specifically good enough for internal representation, things like if you want to use some kind of an encoding thing, so you want a distinct feature representation, then you go for these kinds of distillation techniques. And if you just want to maintain some kind of a relationship, then you go for relation based. I would say, in my experience, what I've been using a lot is more around the response-based knowledge distillation, and we use knowledge distillation heavily in synthetic data generation, practically, not only for model inference, but also for synthetic data generation to do things like fine-tuning. So at a high level, you can see on your screen itself. So you can see the upper layer is the teacher model, and the student and the lower is the student model. An example of this is DistilBERT. So if you've heard about DistilBERT, it's a classic example of how the BERT model has been compressed by 40%, retaining 97% of its performance with a 60% inference speed. It's kind of a win-win for a lot. But this can be done similar for decoding models. I think we have been doing a lot of projects around this for knowledge distillation, specifically in the area of fine-tuning and techniques like RLHF. So I think it's out of the scope for this talk, so I'll not talk about that. So if you look at this teacher-student model, you actually look at the labels or the things that are being split by teacher, and you try to calculate your distillation loss. So obviously, when you're training something, it has to be based on some kind of soft label. So those soft targets are generated by the teacher model, and you train upon that. And you can actually choose either to go with the logic layer, which is the last layers of the network, or you can try to also use it for intermediate layers. So this is a very straightforward example to utilize the knowledge that the really large model has about the world to do this. As just said, that there's also an example for knowledge distillation. You can go through that, and this is a simple implementation to understand how knowledge distillation works. Now, there's also something called as low rank approximation, and people who have been working with matrix multiplication or any kind of traditional machine learning algorithms like LSA or SVD would know this really well, that you can represent really huge matrices into sub matrices. The core idea is that you can decompose these matrices, and the left hand figure that you see is the fine tuning algorithm, which is nothing but LoRa, and the quantized version of this is QLoRa. So there are different ways to do it. We definitely use the SVD and an adaptive rank selection, which is just adjusting different part, but SVD is much more straight to understand, wherein you go and decompose this matrices into three underlying different smaller matrices, where so the underlying representation is much straightforward. Now, what this does, at least in terms of the fine tuning that you see here, instead of a huge number of parameters, billions and billions of parameters that needs to be trained, you are only able to train a finite number of parameters, and you're able to merge it and come out with a model which is much faster. Now, this is obviously a sample like implementation that how the original weight matrices used to look and how it is looking now with respect to how it has been for LRD. Now, all that I have spoken about is more about compressing the size. But when you are dealing with all these high memory and high throughput, low latency kind of application, the thing that you need to optimize is your inference as well. So how do you take these such models and optimize it? Some of the examples that has worked really well for me is batching and speculative inference and model parallelism. So batching, as the name suggests, and this image that you see is the TGI server image of Hugging Face. This actually shows you how a model sharding works. So batching, as the name suggests, is a processing of multiple inputs at once, parallelizing it. But there is a catch here, and the approach here is to handle multiple inputs at once. But the catch is you can't do straightforward batching, because although we are talking about the transformer architecture, mostly what we have been talking about till now is the decoder cycle, which is irregular in terms of handling or the length in terms of handling the input and output, because the length of input and output are very different. So if you look at that, there are different kinds of batching that comes to picture. There is obviously naive batching, which is a fixed number of requests. There is dynamic batching, where the prompts are batched together and on the fly, and then you actually it goes from a uniform length. But what actually is a real good approach here is continuous batching. Now, in continuous batching, what happens is I look at all these requests together, and I kick off at every iteration. I kick off the request that has completely finished. For example, if I say the capital of Australia is Canberra, and then there are questions which are much more longer in length, and the answer is longer in length, what happens is you really have to wait a longer time for that batch to complete. So the moment one of the batches are complete, I kick off that. So in that way, you can actually go ahead and do this continuous batching at a much better scale. The other one, which is something called as speculative inference, and this is really a game changer, because it's also called speculative decoding or blockwise parallel decoding. So what it does is, like, you know that when you do these predictions, you can only spit one token at a time. Now the idea is to spit multiple tokens at once, but that is not technically possible, because when you actually spit the next token, you need to have all the KV values for all these tokens computed, and then the token gets spit out. So here the idea is maybe a smaller model. It looks and spits all these multiple tokens parallelly, and all these are actually verified by a bigger model. All the corrected ones are actually given back to the models itself. The rejected ones are actually discarded. In this way, you have like multiple parallel lines running, one for generation, one for verification, and all comes together. This is how a speculative inference works. You can see this small video or a GIF image that actually give you. So the draft model is what we are talking about, and the target model is actually generating or verifying it. So you can see that these three tokens are generated, and all are validated at once, because now all of these are loaded already in the target model. So Jerry is a cat. Now the cat was not correct, so it has been replaced by mouse. But Jerry is the correct token. So Jerry is given back to draft model, and now mouse is generated. So now parallelly, you can actually work with multiple generation tokens, and this saves a lot of time. So if you look at this technique, this is a game changer for many. The last one is about model and data parallelism. Now, parallelism in LLM context are basically three, two of which are very popular. One is model parallelism. So these weights that you're talking about, if you go to Hugging Face and you download these weights, you can see it's divided into multiple parts. Now, all these weights across multiple layers can be loaded into multiple GPU devices. This is model parallelism. If you take these models and if the same layer, if you take all the tensors in the same layer and put it across devices, it's called tensor parallelism or a part of data parallelism. And the sequence is, we have a lot of sequences that goes in. You have the token coming in, the KV cache getting computed, and obviously the final decoding. So if you split the input sequence and put it across multiple devices, then it's called sequence parallelism. Model parallelism is much more straightforward, and as you see in the images, there is, however, a drawback to that, that it creates something called as pipeline bubbles, which means to say you have to optimize the time in which these losses are computed. So it's something called as micro batching instead of the normal batching. So it is being divided into sub batches, and you see in your figure itself all of these forward passes and the backward grading are computed accordingly. So model parallelism is something very popular, and now we also have tensor parallelism. So this is taken from this is how we can do it in CUDA for MLP, which is multi-layer perceptron, simple neural network, and for self-attention. So here you're actually sharding, and you're doing sharding across the layer itself. So this tensor sits in one, so another tensor sits in another one, and then the dropout or the losses are computed accordingly along with the dropouts. So this is a way to do tensor parallelism. And the last is sequence parallelism, which is actually doing which can be done along with tensor parallelism actually. So parallelism is a concept that you can do. There is an example implementation as usual. So you can go and look into my GitHub. The link will be shared. Now, to all of these, so we have looked at model compression. We looked at all these compression methods and inference optimization. So the things to note from an engineer perspective, or from an AI engineer or an ML engineer, you really need to work or design an application which has low energy and computational cost, which has very less trade-off between latency and the performance itself. So you can't have very low latency and very low performance. So that is the thing that you gain with compression and optimization. Your memory efficiency and scalability is much better. You have improved latency, as I said. This also makes a lot more environmental impact if you look into it. And if you have a chargeback mechanism in your organization, that I think that helps a lot. So it overall helps in reducing the performance complexity. If I can close via case study, so this looks like a rack system, which is very similar to what you have been looking at. This is one of the experiments. I borrowed this diagram from this link, but it's very similar to an experiment that I conducted in my organization, that we wanted to optimize the whole rack cost per department itself. So in order to do that, we implemented these following techniques. So in the LLM layer, in the vector database layer, and basically in the prompt compression layer itself. So if I look at the improvements that we have made, we used the Llama 270 billion chat because we wanted to find some good model, and we used a bunch of these techniques. So we reduced the quantization, we reduced the model size by 75% by using this quantization in our existing hardware. We also tried pruning and found that it helps 40%. Distillation actually helped in model performance, model size reduction by 50%, and the LRA was 30%. In terms of the optimization and inference itself, batching proved out to be really well, where we included by 50% because we have a lot more users, so we had to take care of our buffer inference server had to be really good. We also had this model and data parallelism, specifically model parallelism, and then speculative inference. So just to give you a context, we ended up using quantization and knowledge distillation, and from the optimization, we used speculative inference and batching. So these are the things that we used to finish it off. Now, just to close up on this, these are some of the key takeaways for you going forward, that you would have seen by now that model compression actually reduces your size and cost. It optimizes the way your inference is done in your organization. You can build up a chargeback mechanism, and you can obviously build effective RAG systems or any kind of text to SQL kind of a situation, kind of an application with an optimized inference and an optimized model performance itself. So it's kind of a trade-off between low latency, high throughput, and performance and latency and throughput. So with that, I would like to close and look if you have any questions.
Oh, we actually have two questions.
Okay.
What methods or techniques would you recommend for compressing time series data like stock market data?
A time series is a bit tricky because if you try to solve that, and I'm a big advocate that you cannot use the same kind of LLM model for everything. Although there are architectures for the time series models itself, you can see that there is a class of a model family like TIM, which is basically meant for time series. Those are much smaller as compared to the traditional LLMs. So you only have two options. You can use the traditional stat models, or you can use a TIM size family of models for time series.
Okay, thank you. And one other question that we have is, I'm very green on such a technique. So my question about model compression is whether this technique would decline the model performance like accuracy.
I'm sorry, can you please repeat that?
I'm very green on such a technique. So my question about model compression is whether this technique would decline the model performance like accuracy.
So as I said, when you directly use it, like for example, you just quantize the model and use it in your Google Colab, it would definitely degrade your model performance. So you have to use these techniques in a mix. Although you're using a quantized or a smaller model, you still have to rely on techniques like speculative decoding and specifically knowledge distillation. I would recommend that a lot because that has helped me in my own pipelines. So you're just trying to strike a balance. You would still not match the larger model. So let me make it very clear. But for the use cases that you are looking for, maybe you don't require that much. Maybe you don't require to spend a whole lot of money in API charges and maybe the hardware and get that kind of a performance. So you really have to do your own testing to find out what is the delta that you're having. So I think I can share more about it in my future sessions about what is the cost optimization or ROI analysis that you can do to take a call on that. Or you can always connect with me on LinkedIn.